Next slide, sir. Next slide. 41. Yeah, in this we have done the TG analysis, and you can just observe both type of material is widely temperature stable. Even in ultrasound, you cannot find major losses, weight losses. Next slide. Yeah. In the next slide, you can observe non-ultrasound 500 5000x, meaning a non-ultrasound material 500 calcination temperature and 5000x is a magnification. And the second picture is or second micrograph is non-ultrasound 700 calcination temperature 5000x. So 5000x is a fixed magnification. So non-ultrasound 500 material does not show any kind of behavior of say cubic or tetragonal, while ultrasound 500 calcination temperature material, which is a third and clear picture, shows the clarity and the importance of the material. Even if you give more temperature.
Dr. Deepak,
Can you listen me?
it was broken earlier, but now it is audible.
Yeah. So now I think you can show the earlier slide. But that's okay. That's okay. So this micrograph shows the type of non-ultrasound material, how it looks, and ultrasound material. So what we want to say here, the size reduction using ultrasound is been it can be visualized. Next slide. Next slide. 44.
44 is there.
Yeah. So in this slide, you just look how the ultrasound plays an important role. Very small type of, this is a 100x or 100x magnification material, and the size reduction is been you can easily observe, and this is why the ultrasound is more important. Next slide. So we have done the energy calculation based on the changes of the phases, and net energy save is close to 28% in this operation, which is again I would say huge. Next. Yeah. So considering the concluding part here is we have to give just a 10 minutes of ultrasound to the reaction media, which increase this higher yield. So the time reduction is mainly observed here, while the close to 30% is the energy save. Next. With the same way, we have also done the cerium oxide synthesis nanomaterial. Again, it has many advantages. Next. Next slide, sir, please. Yeah, in this slide number 48, you can easily observe the same way we have a again I would say this is a precipitation type of technique. Cerium nitrate and NaOH has been taken, and we have given we have varied the percentage amplitude and reaction time, and you can easily synthesize Syria material, which is very important. Next. In this slide, you can just observe the ultrasound material as against the non-ultrasound material. So you need 4 hours reaction time to complete this reaction if you are using conventional, either say magnetic stirrer or overhead stirrer. While we need to give 20 minutes. Now the 4 hours 20 minutes are the optimized parameter which we have put here. But again, it has been uh, this parameter have been fixed after varying the reaction time of the conventional as well as ultrasound material. Again, the yield has been improved, the crystallinity has been reduced, and the crystallite size we have observed in case of Syria is 6 nanometer. Next, in TJ analysis, we have found that ultrasound material have a lower temperature stability as compared to the non-ultrasound, and one of the major reason is here we can say that the nucleation process is so faster that the material stability has been lost. This is what our prediction was. Next. These are some of the micrographs, and at 500 magnifications. One is the A belongs to the non-ultrasound and B belongs to the ultrasound. You can observe here, as against the non-ultrasound material, ultrasound gives the sharp edges and clear picture. Next. This is how it looks when it has a 10,000 X material. And in the next slide, in the next slide, you can observe here at 30,000 X. Next slide. We have also done the energy calculation for this type of material, and considering 4 hours as against 20 minutes, you can easily save up to 92% of energy, which is again huge. Next, in the concluding part, as like any zirconium material and zinc oxide material, we can easily synthesize this material using the precipitation method, saving a lot of energy and with increasing the reaction yield. Next part. In the next part, it belongs to the Sol-Gel techniques, and we have considered or we have received this case, I would say, considering the titanium, considering the importance of the material. Next. Next slide, sir, please. Again, next. Next. Yeah. So in this slide, our importance, we have received one of the sample from Thane industry, and it was anatase type of material, and they were interested to convert this anatase material into the rutile. Now you will be confused with the TiO2 because many of you must have used TiO2 material for as a catalyst for the wastewater industry for degrading many uh, compounds. While rutile, if you observe, this rutile type of material is been used for exterior coating of the building. And why two types of this material? Because one anatase type of TiO2 under the UV radiation degrade the materials, while TiO2 rutile type and blocks the UV rays. So one material, if you give some physical changes, can be considered for many applications. One blocks the UV rays, and one use the UV rays for the further degradation. Next. Next, sir. Yeah. So this polymorph uh, has a wide applications, and as far as the rutile TiO2, DuPont has major monopoly in the world. So that company was interested to understand whether using small quantity of any kind of energy, whether we can convert this material into rutile or not, and this was their interest. Next. So in this in this reaction, we have taken titanium tetraisopropoxide and acetic acid and 2 propanol, and we have prepared the sole, and we have given the additional 10 minutes of ultrasound, and at the jail condition, again we have given uh, ultrasound for 10 minutes. Next. So in this sonication time for conventional, we can consider as a zero, because in sonochemical we have given additional 20 minutes. So we our close observation is we can easily increase the yield up to 93%, while we haven't observed any kind of differences in the crystallinity, while the crystallite size was reduced. And the more important here is the calcination temperature, which required for say converting anatase to rutile for conventional method was 850, while if you put 20 minutes of additional ultrasound, it is reduced to 750 degrees centigrade. Next. Next slide, sir. Yeah, these are some of the XRD patterns for non-ultrasound and ultrasound materials, and as like the same method of the XRD analysis, which we have utilized for in case we have used for zirconia, the same technology is been used for calculating the XR crystallite size as well as crystallinity. Next. So in this, only the 2 theta 25 degree corresponds to anatase, and 2 theta 28 corresponds to rutile. Was the yeah, in case of zirconia, 2 theta 29 and 31 degree for monoclinic, and 2 theta 30 degree for tetragonal was we have taken for zirconia. And in this case, it 25 degree for anatase and 28 degree for rutile. Next. So this is our specific observation. In fourth column, you can just look for percentage of rutile. Non-ultrasound 450, it is 0%. Non-ultrasound 550, it is 550. Non-ultrasound 650, 29 percentage of rutile. Non-ultrasound 750, it is a 71 percent, and non-ultrasound 850, it is 100% rutile. So in case of ultrasound, the same column, if you look observed at 750 ultrasound, it is 100% rutile, and this was the close observation which XRD graphs has given to us. Next. The same way, the observation of ultrasound at 2000 x, which we have observed. Please go to the next slide. Yeah, this is very important slide. Non-ultrasound 850 is close to 10,000 at 10,000 x magnification. It looks, even though it's rutile, it still looks like a fluffy material. While at 750 degrees centigrade, ultrasound material shows building block kind of structures, which was important study or important observation happen after using the ultrasound for say 20 minutes. Next. Again, we have done some calculation here, and almost say 70% energy has been saved to for just converting anatase to rutile using the ultrasound material. Next. In the concluding part, for the sol gel, in case of TiO2 material, the yield was increased by almost by 10%. And again, as I said, 100-degree temperature has been reduced by addition of 20 minutes of ultrasound, and which has saved more than 70% of material. Next. The last part is the solar energy, which we recently we are trying to explore, and there are interesting story associated with this. Again, I don't want to give major introduction about this section because everybody knows the importance of the solar energy as on today. And in this, the main type is the ultraviolet, which is close to 280 nanometer wavelength, while the near IR is around 4000 nanometer. So we have used the combination of photochemical energy and the thermal energy for the chemical synthesis of the nanomaterial. Next slide. Yeah. In this, you can on the right side, the picture belongs to the setup which we have designed indigenously, and the left side is just a schematic diagram. And the interesting story behind is the use of Fresnel lens. And when I joined the position in ICT, it was way back in 2013. I joined. That time, I was going through some of the scraps in the scrap areas, and we receive OHPs, overhead projector, and we have broken those OHP and we got those lens. And it was just a curiosity, being a young faculty at that point of time, whether we can concentrate some of concentrate Mumbai. I would say Mumbai sun rays, and whether we can synthesize some of the particles or not. That was our interest. And in the further slide, you can easily observe that we can easily did the job. Next. Next. Case studies. Next. Okay. So our first case study was whether we can convert this material into any value-added material or not, and using solar rays. So concentrated solar radiation was the concept which we have come up in the market using Fresnel lens. So we have taken zinc acetate anhydride and glycol, and we have put this material directly into the beaker, simply beaker, and we put Fresnel lens above. And for our wonder, zinc oxide nanoparticle has been synthesized. Then our investigation start why and how and what are the differences. So again, like ultrasound or the cavitation area, there are chances that our prediction was the hotspot generation has been observed. Then definitely we have check using the hydrophone that there are pressure changes, because the tip temperature goes up to around 700 degrees centigrade. If you closely observe about this concentrate solar radiation on one particular, but the effective temperature difference was not more than say 20 to 25 degrees centigrade. Next slide. We have done the again synthesis of the palladium nanoparticles. Next. We have also tried using the CSR, that is concentrated solar radiation, whether any kind of ferromagnetic particle can be synthesized, and which was easily synthesized in our case. Next slide. Then again, we thought it whether during the synthesis of the silver nanoparticles, by putting any color type of filters or the films, the specific wavelength can be given to the solution media. And say without filters, we have without filter, with filter, we have observed various average particle size. So without filter, it was close to 295. When we use the pink filter or the pink film, it was 211. Blue, it was 275. Green, 350. Yellow, 272. And in red, 363. And it is definitely associated with the wavelength which is been given to the reaction media. Next. Next slide, last slide. Yeah. So this is in the early stage, and definitely with the help of Professor Shriram Sonawane from VNIT, Professor Shiri Sonawane from VNIT Warangal, Professor Pandit from ICT, definitely we are looking to develop this type of technology for industrial scale. And during the, I would say at the lab scale, it is but scaling up at the industrial scale is challenging in this area, while the hydrodynamic and acoustic cavitation is well established in an industry for many applications. So I think our next target will be developing solar based technologies for the chemical synthesis for organic as well as for inorganic synthesis. Challenge, next slide. And challenges are there are a lot of challenges in this area, but again I would say there are a lot of opportunities associated with these areas. And as I said, using this like-minded scientists all over the world, we can look up for this technology, because the cost of the electricity is so high. And again, solar is free of cost for us. We have to just design the setups, we have to just play with the setups for the benefit of the industrial as well as for the mankind applications. Last, thank you. Thank you for listening patiently, all the participants. I really appreciate the way you responded us, and I especially thanks Professor Shriram Sonawane for coordinating this session, because in between the slides stuck up and he has to play his role, and I really appreciate the way he handled his job. Again, I thank VNIT Professor Umre for giving this opportunity. I must appreciate all my gurus, collaborators for this wonderful work and for this stage of my life. Thank you. And my students.
Thank you very much, Dr. Deepak.
Yeah, please,
So,
sir.
dear participants, Dr. Deepak has delivered very uh, fruitful lecture. The lecture was very fantastic, and he has focused on so many his research things, even some patented things I could have seen. So, Dr. Deepak, thank you very much. I am hoping on behalf of AICT Atal, on behalf of VNIT, and on behalf of all participants are from teaching background and some of from research background. So I must thank you on behalf of all. Thank you very much.
Yeah. If there are any questions, please.
Yeah.
Otherwise, you can just.
If you could open, Dr. Deepak, if you could open your
I
chat
cannot.
box, you could see some Q type of questions.
Can you read it, because I'm using the mobile?
Okay. So one question I could read: comparing acoustic and hydrodynamic cavitation, which is better?
It's depend upon the applications. If you look, hydrodynamic is for the large scale or the bulk scale operation, and acoustic is for a small scale operations. So depending upon the applications, we cannot say this is better or that is better. We cannot say. But if you have the fixed volume, or the small volume, the acoustic is better. And if you are looking for the large volume, hydrodynamic is better.
There is one question. What are the improvements in properties other than saving energy and time consumption using ultrasound a technique?
Ideally, it was our there are the improvement of the properties which have been already shown here. A few of the properties, say thermostability, then the nature of the materials, which has been, say, in case of TiO2 material, which we have used for exterior coating, and those results I have not put here, but we have found that the UV radiation is been blocking of the UV radiation is been increased in case of ultrasound as compared to the non-ultrasound material. So there are many type of benefits considering the physical properties of the materials. But in this work, when we started this work, our interest was whether we can process intensify this kind of work. Yeah. Next.
There is one question: how TiO2 uh, futile act as UV blocker?
I think it's better you just Google down, because
How TiO2 rutile act as UV blocker?
yeah, it's a property of the material. Now I don't have the chalk and pens. Otherwise, I would have seen. I would have chalked down and would have seen. You just Google down the question. Who have maybe the participant? Just to Google. It's a simple methodology how it gets blocked.
Another question is: what is role of filter in case of silver nanoparticles?
It was our interest was whether using different filters, any particle shape and particle size is getting changed or not. So, as such, there was no big study considering the filters. It was just understanding if you are using, say, pink type of filters at a specific wavelength, you can get the other type of or different type of shapes. But considering the shape, it was of no change.
There is one question: what is the relationship between ultrasonication time and the calcination temperature? Does in all the cases the calcination temperature will decrease or increase along with ultrasonication?
Can you repeat the question again, please?
What is the relationship between ultrasonication time and calcination temperature? Does in all the
See,
cases.
for any process intensification work, I'll take this question by first. See, for any process intensification work, we need to optimize the reaction time first. So at specific reaction time, then we have varied the calcination temperature. So we cannot say there is as such relationship between irradiation time and calcination temperature.
So the similar question with this question: does in all the cases the calcination temperature will increase or decrease along with ultrasonication?
It will not increase because if your reaction time is fixed, once the reaction parameters is optimized, then the received material is being calcined at different temperature. Any another questions?
Yeah, there is one question I could have seen. Nanotech pervades all sectors, and there is a huge range in riskiness between the application. How can we develop a meaningful triage system to prioritize sectors? This is general question basically. This question should not be answered. It's okay. So, Dr.
Yeah,
Deepak, thank you very much. Thank you very much for delivering the lecture.
yeah. Thank you, Professor Sonawane.
Thank you. Thank you all participants.
Yeah,
Join next session at 2:30.